Okay, inverse trig functions in this video, and we're going to learn how to take the derivatives of them. And this is going to be probably less than pleasant for you because these formulas are going to be a little gross, but that's okay. They're just formulas that you have to know. And then once you know them, the questions that we'll see actually, aren't super terrible, but the formula is. All right, here we go. Remember, there's domain restrictions whenever you're doing an inverse trig function. And by the way, arc cosine, that's the same thing as cosine inverse. Arc sine, that's the same thing as sine inverse. Same thing, right? With tan inverse. And then all these other ones, you could write it with the inverse notation with the -1, or you could write it with the arc notation. The arc notation is probably better because then you're not confused about inverse versus reciprocal, but whatever. Arc sine is the same as sine inverse and same for all the other ones. But whenever you're doing an inverse trig, you need to make sure you are spitting out the correct angle. For instance, like we have arc sine of -1/2. So if I'm thinking about my unit circle, I know sine, I'm looking, this says there's some sine of some angle, and we know the sine ratio of that angle is 1/2, and we're trying to figure out what that angle is. Now, oh, sorry, it was negative, wasn't it? Now there's 2 points on the unit circle that have that correct sine value, right? That have -1/2 as the y-coordinate, right? There's this one and this one. However, when you are doing inverse trig, we want it to be consistent. We don't want to sometimes get this angle and then other times get the different angle. We want the inverse trig to be a function, so we want it to always consistently give us the same output for this input. So that's why we have the purposes of these. That's what the purpose of those domain restrictions are, so that it will always behave consistently. Cosine, secant, and cotangent. Anytime you do one of those inverse trig functions, you will always get an angle either in quadrant 1 if it was a positive term, or in quadrant 2 if it was negative, right? So it's just 0 to 180, or it's 0 to pi. Those are the restrictions for the angles that an inverse cosine, an inverse secant, or an inverse cotangent would go, right? And cosine and secant are reciprocals of each other. Sine and cosecant are reciprocals, and then the tangent and the cotangent get split up because of the undefinedness of where those points make you divide by 0. Yeah, cosine inverse and its reciprocal, along with the cotangent inverse. When you do them, they should always give you an angle either in quadrant 1 or in quadrant 2. However, for the sine inverse, for the cosecant inverse, or for the tangent inverse, you should always get an angle in quadrant 1 or in quadrant 4. So for instance, for this question, we wouldn't care about the stuff over there, right? We would want to get the angle in quadrant 4, and instead of naming it as 11 pi over 6, instead of naming it with the big positive angle, you would name it with the negative angle instead. So our domain restrictions for the sine inverse, the cosecant inverse, and the tangent inverse, it's always quadrant 1. If this was a positive ratio, right, you would have something in quadrant 1, or for any of these, if you have a negative ratio, it would be in quadrant 4. But instead of using the big positive angle, you would use the negative angle instead. Okay, so sine inverse of -1/2, or arc sine of -1/2, what angle has this as the y-coordinate? We're going to always get the negative pi over 6. There's other angles that will also satisfy that, infinite many angles because of the coterminal angles you learned about in pre-cal, but specifically when we're doing arc sine, or when we're doing a sine inverse, we always want to consistently give it the same one, either in quadrant 1 if it was positive, or in quadrant 4 if it was negative. And remember, instead of doing the big angle, you would do the negative angle instead. And then for your cosine and your secant and your cotangent, it would be in quadrant 1 if it was positive, quadrant 2. If you're doing like a cosine inverse of a -1/2, you would have the 2 points on the unit circle, but you would want the one in quadrant 2. Okay, so the inverse trig restrictions apply so that we always consistently will get the same thing. Like here, cosine inverse of -√2/2, there's 2 points on the circle that work. However, we would care about the one that was either in quadrant 1. If that would have been positive, it would have been in quadrant 1, but since it's negative, you'd want the one in quadrant 2. So that one would be your 3 pi over 4. And then arctan of -0.3, that's not a unit circle value. If it was like a square root of 3, or if it was an arctan of 1 or -1, then you could use your unit circle. But this would just be something that you would have to use your graphing data calculator. Just hit second tangent, and then you would get your angle as -0.291. And remember, we would pretty much always want the angle to be in radians Very, very rarely ever would you want it to be in degrees. All right, so now let's kind of do a little bit more pre-cal review, and this stuff is going to help us because when we go through and derive these formulas for the derivatives, we're going to use a similar process. So it says evaluate sine of arc cosine of 4/5. And you're like, okay, Mr. Bell, 4/5 is not a unit circle value. So I don't know what this angle is. Well, that's okay. You don't really even need to know what the angle is. What we're going to do is use the stuff inside to make a reference triangle. Now, since 4/5 is positive, I know that reference triangle is going to be in quadrant 1. I don't know what the angle is. If you want to call it like theta, that's fine. Or if you want to call it y, that's fine. But here, this inverse trig, right? Inverse trig will always give you an angle. So I have some angle. I don't know what it is, y, but I have some angle, and the cosine of it is 4/5, right? Cosine of y is 4/5. So here we go. I know the adjacent side, thinking about your SOHCAHTOA. Since arc cosine of 4/5, that's going to give me some mysterious angle. That means cosine of y is 4/5. That means this has to be the adjacent side, and then this has to be the hypotenuse side. So 4/5. So we use that inside piece, the inside ratio, to label two of the sides of the triangle. Pythagorean theorem will tell us what the third side is. And then now that I have this triangle complete, right, now what I'm doing is just the sine of this angle y. Now, you never need to know what the sine of y is. Like, you could do an inverse tan or an inverse whatever, right? You could find what that angle is using a calculator, but you don't need to know it because you're going to end up doing the sine ratio of that angle anyways. And sine, SOHCAHTOA, is opposite over the hypotenuse. So the sine of this angle is 3/5. So the strategy is to use this ratio and that trig function, or the inverse trig, to label two of the sides of the triangle, complete the triangle by using Pythagorean theorem, and then apply then the outside trig. Do whatever new ratio we want. Opposite over hypotenuse gave us the 3/5. Okay, so use the inside stuff to make two of the sides of the triangle, complete the triangle with Pythagorean, and then whatever this outside function is doesn't matter. Like if this was a tangent, it would have just been 3/4. Or if it was this cotangent, it would have been 4/3. This outside piece doesn't really matter. Use the inside one to make the triangle, and then whatever other trig ratio it wants you to do, so be it. Okay, now the next one's going to be a little bit harder because instead of it being a ratio of two numbers, it's x, aka x over 1. So we're going to do the same thing. We're going to have this angle y. And the cosine of y is x over 1, so that means the adjacent side is x. The hypotenuse side is 1. Remember, if you see a whole number, you could always write it as a ratio by putting it over 1. And then we're going to do Pythagorean theorem, this squared minus this squared, and then you would square root it to get that third side. So it's going to be the square root of 1 minus x squared, right? It's always the hypotenuse squared minus the other leg squared. That's how you would get an expression for that missing side initially. And then now I would do the sine ratio of that angle y. So sine would be the opposite over hypotenuse. So it's going to just be the root of 1 minus x squared. That's what sine of arc cosine or cosine inverse of x would be. Use this to build two of the sides of the triangle, complete it with Pythagorean, then you just do the outside trig of that reference triangle, no problem. Last one, and then we'll start getting into these derivative formulas. Again, this is going to just be some angle y. My tangent ratio, so here it says tangent of y is 3x over 1. I just didn't write that, so cosine of y was x over 1. It's positive. We like it when stuff's positive because then I know it's in quadrant 1. Tangent's opposite over adjacent. So the opposite side is 3x. The adjacent side is 1. That means this hypotenuse, I would do this squared plus this squared, and then I would square root it. So I would have the square root of 1 plus 3x squared. And then the secant is the reciprocal of cosine. Cosine's adjacent over hypotenuse, so it would be 1 over the radical. That means the secant would be the hypotenuse over the adjacent, right? It'd be hypotenuse over adjacent since it's the reciprocal of the cosine. So it's going to be the radical over 1. So you could write this as either 1 plus 3x in parentheses squared. That would be fine. Or if you wanted to drop, I was off the screen. Sorry, so close. I was doing good and I messed it up. Oh well. 1 plus in parentheses 3x squared, or you could have 1 plus 9x squared. Either one of those would be fine. The common mistake that I see people do is they'll drop the parentheses, but then they'll leave it as a 3. That's not right. If you're going to drop those parentheses, you're going to have to take that stuff and square it. So if you drop the parentheses, it should be a 9x squared, right? Not the 3x squared. Be careful. That's a common mistake. Either that or that is fine. I don't care. Leave the parentheses or multiply it out. I don't care. Just make sure you don't drop it and then not multiply it out. Okay, so those skills, what we just did in those 3 examples, that's going to come up in the same type of I guess skill method as we're going to see when we're proving these derivatives. So let's go for it. It's going to be a little bit confusing, but at the end of the day, they're just formulas you will have to know. Okay, here it says we're going to derive the formula for the derivative of arc sine. So we're going to have sine inverse of x, and we're going to find what the derivative of it using a similar process to what we just did. Okay, so here y equals, I always like the inverse notation a little bit better than the arc notation. That's just my own preference, but it's whatever. So I know y is the sine inverse of x, and we're trying to find y prime, right? The goal is to find what is y prime equal to for all of these, for sine inverse, for the tan inverse, and then on the next page we'll do the secant inverse. Okay, and how we're going to do it is going to be similar to what we just did, right? Now, I'm going to go ahead and take a sine on both sides. So that means sine of y equals x. And then I'm going to use this, or that's x over 1. I'm going to use that to make my little reference triangle. So I have this little scratch work. Come on, pen. Don't be dying. You're like a new pen. So I have this little reference triangle. It's a positive ratio. My angle is y. And then the sine ratio, which is opposite over hypotenuse, since the hypotenuse isn't written, it's just 1. So x over 1. And now, again, I'm going to use this. Got 2 of the sides. Use Pythagorean theorem to get the third one, 1 minus x squared. So I use this little step to make the reference triangle, and I'm going to just kind of leave that off on the side for a minute. We're going to come back to it, but in just a minute. Now, what we're going to do is we're going to take the derivative, right? We're going to differentiate with respect to x. Now, it's going to be implicit, but that's okay. Here, the derivative of sine of y would be cosine of y, y prime. And, of course, the derivative of x is just 1. Okay, so then what you would do is try to get the y prime by itself. So you would divide by the cosine, 1 over cosine y. Now, 1 over cosine y, that's the same thing as secant of y. And then if you wanted to, you could reverse substitute. And instead of it being y, you could write secant of sine inverse of x. And then here, that looks just like what we just did in those previous 3 examples. But we don't really want to leave it like that. That's terrible. Right, what we're going to do is just go pull the secant ratio of that angle y, right? We've got that little scratch work already done. Instead of writing it like this, which would be awful, we're now going to go pull the secant ratio of that angle y. And that's what our derivative is going to be equal to. Okay, so here we go. The secant, remember, cosine is adjacent over hypotenuse. So then the secant is going to be the hypotenuse over the adjacent. So it's going to be 1 over the square root of 1 minus x squared. And if your original function y is sine inverse of x, then the derivative, y prime, is going to be 1 over the square root of 1 minus x squared. So there's your derivative formula. It's nasty, I told you. The derivative of sine inverse of x, it's 1 over the square root of 1 minus x squared. It's not a very nice derivative, but this is just something that you will eventually just need to know. Right? Those inverse trig ones, they're just kind of ugly, but you need to know them. All right, let's do the same process to find the derivatives of inverse tan, and then on the next page we'll do the inverse secant. Here we go. We could rewrite this. I have y equals tangent inverse of x. That's not really doing anything. That's just visually rewriting it. So I know tangent of y is equal to x. Let's go use this to build that little reference triangle. The angle is y. Tangent's opposite over adjacent, so the opposite is x. The adjacent's 1. That means the hypotenuse is going to be 1 plus x squared. Okay, so we've got the little reference triangle. Now we can take the derivative. The derivative of tangent is secant squared. So secant squared y, y prime. Of course, the derivative of x is 1. And then divide it over. So I've got y prime, which is equal to 1 over secant squared y. Secant squared on the bottom, that's the same thing as a cosine squared on the top, right? Since cosine and secant are reciprocals of each other. So what I'm going to do is I'm going to go find what the cosine ratio is, and then I'm going to have to square it. So let's go pull the cosine of angle y using this reference triangle, and then we'll just square it. Okay, so cosine is adjacent over hypotenuse, so it's going to be 1 over the radical. 1 squared is just 1. And then if you have the radical squared, the square root and the exponent are going to cancel. So I have 1 plus x squared on the bottom. And there we have it. If your original function is tan inverse, or arctan, then your derivative is 1 over 1 plus x squared. There is your derivative of your inverse tan. It's going to be 1 over 1 plus x squared. That one's not actually super terrible. It's not nice, but it's not terrible. The sine inverse is kind of gross. The tangent inverse one, it's not terrible. Okay, and then let's do the same process one more timesies, just for fun. Really, it's to get the secant inverse. Don't look at the box. Don't look at the box. Here, let me cover it up so we don't spoil everything. Although, you can probably just pause the video if you really wanted to. Oh well, just don't look at the box. We'll talk about that in just a minute. We're going to go through and prove the derivative of the secant inverse using that same process. Okay, so here we go. We've got secant inverse of x. So that means secant of y is equal to x. Now, you could use this ratio to build yourself the little reference triangle. Well, that's great. And then you could go through and you could take the derivative, but you know the derivative of secant is going to be secant tangent. So you have secant y, tangent y, y prime is equal to 1. And like that'll work, and that'll get you the answer, but you'll have more stuff to go pull in from that reference triangle. So instead of using secant, I'm just going to use the reciprocal. If secant of y is equal to x, then that means cosine of y is equal to 1 over x. Right? Either one of those is fine, and either one of them, if you use it to generate this little reference triangle, either one would give you the same. Secant would be the hypotenuse over the adjacent, so x over 1. Cosine's the adjacent over hypotenuse, but that side's still 1, and that side's still x. Right? Either way, both of those would generate the same thing, and then you'd have to do Pythagorean theorem to get this third side, which would be the square root of x squared minus 1. It's always the hypotenuse squared minus the other leg squared. That's how Pythagorean theorem works. In case you didn't know that, you're welcome. Okay, now I would rather take the derivative of cosine than secant. That's just my own preference. You can take the derivative from this point. You just have slightly different middle steps than me, but we'll eventually get to the same thing. But now I'm going to go through, and I'm going to take the derivative. The derivative of cosine y would be negative sine of y prime, and the derivative of 1 over x is negative 1 over x squared. That's just a power rule. Now the two negatives will cancel, which is lovely. I'm going to divide the sine over. Let's pick this sucker up over here. Am I still on the screen? Oh, I'm doing so good today staying on the screen. I'm going to jinx it, I'm sure. So I'm going to get y prime is equal to, the sine will go to the bottom, so I have 1 over x squared times the sine of y is on the bottom. You could change that and put a cosecant of y on the top if you want, but I'm just going to leave it on the bottom. And now we need to go pull what that sine ratio is. So I have 1 over x squared, and then I have to go get the sine ratio of that angle y from my reference triangle. Sine's opposite over hypotenuse, SOHCAHTOA. So the opposite side is the radical. The hypotenuse side is x. So we'll have the square root of x squared minus 1. Sorry, it get kind of small. The square root of x squared minus 1 over x. And then there you have it, right? That if your original function is secant inverse, here's your derivative. But we could reduce that a little bit, right? So this derivative, still 1 on the top. And this x, it's going to cancel with one of those, right? So we could reduce it. That x will cancel with one of those. You're still going to have an x. And I'm still going to have the radical with x squared minus 1. So that's what the derivative is going to look like. But there's a little wrinkle. Just to avoid any weird domain issues and switching quadrants or anything, remember what I just had in this derivative, right? What the derivative was equal to. Oh my gosh, I just smeared it. Oh well. This bottom left chunk, right, since it's x squared, that bottom left chunk is always positive. When we reduce it, we kind of need to make sure that that bottom left chunk also stays positive. So we're going to just put the absolute value around it. Okay, so when I reduce it, when I cancel that with that, I just want to make sure that that bottom left chunk stays positive, so that way nothing weird happens with switching quadrants or getting the wrong angle from the secant inverse. We're just gonna keep that bottom left term positive, putting the absolute value. All right, cool. Now there's your derivative of secant inverse. It's ugly, but your derivative of secant inverse is 1 over the absolute value of x, and then you have the square root of x squared minus 1. Right? Not pleasant at all. Right? Those are your three formulas for your inverse trig. I know you're like, whoa, Mr. Bell, there's 6 inverse trig functions. We just did sine, tangent, and secant. What about the other 3? What about the cofunctions? Well, what's nice is this box is going to make us see is that the cofunctions really aren't new in and of themselves. They're just the negative versions. So your derivative of sine inverse is the same thing as the derivative of cosine. The only thing extra that your cosine has, right, since it starts with a c, if it's arc cosine, if you can rewrite it as cosine inverse, then it'll start with a c. But all of your cofunctions, we know, have to be negative. But the cosine inverse derivative is the same thing as the sine inverse derivative, 1 over the square root of 1 minus stuff squared. The only thing different is the cosine inverse will be negative. Your tangent inverse, right, it's 1 over 1 plus stuff squared. Du dx just means do chain rule, right? This piece right here just means do chain rule. And the cotangent is the same thing, but negative. Here's your secant inverse derivative. The cosecant is the same thing, but negative. Right, so we have 6 inverse trig functions, but there's really only the 3 formulas, and then just remember if it's a cofunction, if it starts with a c, to put the negative as well. Now here's typically how I remember them, right? That's kind of ugly. How I remember them is like this. Okay, this is what you would probably want to make note cards for. Just taking these derivatives, sine inverse of stuff. When you're taking the derivative, it's going to give you 1 over the square root of 1 minus stuff squared. Okay, that's your formula. And then whatever was inside copies inside. And then you think to yourself, as I copy that inside piece, is the derivative of it 1? If the answer is no, you would need to do chain rule. Typically, you're just going to stick that chain rule in the top. That's all they did, right? That's all they had here. They had 1 over the square root of 1 minus stuff squared. They had the chain rule written on the right. You can put it on the top if you want. But that's your formula. 1 over the square root of 1 minus stuff squared. Whatever was inside copies, then you do chain rule, stick it on the top. Here's your formula for your sine inverse. And of course, if you had the cosine inverse instead, all you would need is the negative. Okay, tangent inverse of stuff. Tangent inverse is the nicest of these 3. It's 1 over 1 plus stuff squared. Whatever was inside would then copy, and then you think, okay, as I copy that, do I need to do chain rule? If the answer is yes, then you just stick the chain rule derivative in the top. And if it would have been a cotan inverse instead, again, all you would need is the negative. Tangent inverse is the nice because there's no square root, right? No radical, and it's addition. So if you wanted to, you could flip the order in that denominator, right? It doesn't make any difference. But usually I write 1 plus stuff squared, but you could just as easily do stuff squared plus 1. Doesn't matter. And then the cotangent is the negative version of it. Last one, the secant inverse. And then we'll finally get to some examples. We have the secant inverse, or arcsecant. If I have secant inverse of stuff, this is the worst one. Right? Tangent's actually not too bad. The sine inverse is like, but the secant inverse takes the cake. It's 1 over. You have the absolute value of stuff, and then I have the square root, and the order is reversed. For the sine inverse, the constant comes first, then you subtract the variable. For the secant inverse, that order is going to be backwards. It's going to be stuff squared minus 1. And then whatever was inside your secant inverse would copy here and would copy here, and then you would need to do chain rule in all likelihood, and if so, you would just stick that chain rule derivative on the top. And if it was a cosecant inverse instead, remember, all you would need is the negative. So those are your 3 formulas, right? What it says, you can pause the video if you want to copy those down. If you weren't doing that, you probably should have been, but you'd want to copy those down. That's really just the same thing that this box says. I just think that looks a little bit nicer I think about like sine inverse of stuff, 1 over the square root of 1 minus stuff squared, or tangent inverse of stuff, 1 over 1 plus stuff squared, secant inverse of stuff, 1 over the absolute value of stuff, then the square root of stuff squared minus 1. Make sure you get the order of the subtraction right. For the sine inverse, the constant's first, then you subtract the variable chunk. For the secant, the variable comes first, then you subtract the constant. For the tangent, it doesn't matter because it's addition. All right, so those are our formulas. Let's now finish the rest of this page, and then we're done. All right, they're ugly formulas, but at the end of the day, if you know the formulas, you just plug and chug, you use the formulas. Alrighty, here we go. Sine inverse, arcsine, sine inverse, same thing. Arcsine of 2x, just going to use the formula. I've got 1 over the square root, 1 minus stuff squared. Whatever's inside would copy inside. And then I know the derivative of that thing, right? What I just copied, that derivative's not 1. So I'd put that chain rule derivative on the top. And if you wanted to leave it like that, like that's fine. No one's gonna yell at you. But if you wanted to reduce it, you could. You'd have 2 over the square root of 1 minus. Do not say 2x squared, right? Do not say it. It's 2x in parentheses squared. Or if you drop the parentheses, it would be a 4x squared. That's probably how you would see it on a multiple choice question. You can leave it like that on a free response. No one would care. If you drop the parentheses, make sure you square the number that was inside of the parentheses. Okay, next one. We have the tangent inverse. So that's 1 over 1 plus stuff squared, right? There's your formula for the tangent inverse. Whatever's inside, copies inside. Then you do chain rule, and you could stop. Or if you wanted to simplify it, you'd have 3 over 1 plus 9x squared. Again, either leave that as 3x in parentheses squared, or you could write it as 9x squared. Okay, and then here we have arc secant, so secant inverse of e to the 2x. Ooh, fun stuff. All right, so it's 1 over, you have the absolute value of stuff, then I'm going to have the square root of stuff squared minus 1. There's my formula. Whatever this is, it's going to copy. And then I would need to do chain rule. The derivative of this would be 2e to the 2x. So that would, that's fine. That's mathematically equivalent. If you wanted to reduce it, you could. That's actually going to reduce with the exponential on the top, leaving you just the 2. And then that bottom left piece actually kind of just disappears and goes away. That's lovely. And then here, if you have e to the 2x squared, if you have a power to a power, what you would do is multiply those two things. So you would have not e to the 4x squared, you just have e to the 4x, right? A power to a power. Like if you had x cubed to the 5th power, right? That would be the same thing as x to the 15th. Right? If you have a power to a power, you would multiply those numbers. The same thing applies here. 2x times 2 is 4x, not 4x squared. I know it's tempting to take this and square it, but that's not following your exponent rules. So here is how you would probably see that answer if you wanted the most simplified version of it. Again, there's nothing wrong with leaving it like this, but if it's a multiple choice, you would just need to recognize that that's the same thing. Okay, 2 more, and then we're done. This lesson's actually not even being too long. Here we go. We've got cosine of arcsine of 3x, and it wants us to take the derivative. Oh, goodness. Okay, so we have a composite, right? We have cosine of stuff. So we've got cosine of stuff. Then that inner piece is your sine inverse of 3x. Okay, so it's a 3-layer composite, but I'm kind of combining those, right? Instead of doing sine inverse of stuff, I'm just combining those 2 layers into just sine inverse of 3x. Okay, so we could do this derivative with just brute force. The derivative of cosine would be negative sine. And then whatever was inside of the cosine would be inside of the cosine's derivative. So that's your sine inverse of 3x. So now that layer has been accounted for. The derivative of cosine is negative sine. And then we would need to do the derivative of that inside piece. And the derivative of sine inverse would be 1 over the square root of 1 minus 3x squared. I'm gonna go ahead and drop the parentheses, and chain rule says I would need a 3 on the top, and then I would have a 9x squared down here. So that part right here is your derivative of sine inverse of 3x, right? It'd be 1 over the square root of 1 minus 3x in parentheses squared. I'm going to drop the parentheses, so I got the 9x squared, and of course the chain rule puts the 3 on the top. Now let's see what would happen. The sine of sine inverse, since those are inverses of each other, they're going to cancel. Now, the 3x doesn't cancel, and the negative doesn't cancel. So the negative and the 3x, that's going to all combine up here, and I'm going to have a negative 9x, just a negative 9x, over all of this stuff, the square root of 1 minus 9x squared. That one's a little rough, right? That one's a little harder. You didn't have to do it that way. If you remember back to some of the examples we did at the beginning, we could actually do some pre-cal stuff with this, right? We could treat this as y, and we could say, okay, arc sine of 3x, that's some angle y, so I know the sine of that mysterious angle y is going to be 3x, aka 3x over 1, and I could use that to build myself that little reference triangle again. Now the sine ratio is opposite over hypotenuse, so 3x over 1. Then I would use Pythagorean theorem, so it's going to be 1 minus that squared, so 9x squared. Right, so always the hypotenuse squared minus the other leg squared. And then, hey, that's the angle y. And then I could do the cosine of that angle y. Cosine's adjacent over hypotenuse. So this original function, which is the cosine of arcsine of 3x, just like how we did it earlier in this video by just pre-cal skills rewriting it, the cosine of that angle y, well, here's the trig ratio, here's the trig triangle, that's redundant kind of, trigonometric triangle, but I need the cosine ratio of that triangle based on the angle y, and cosine's adjacent over hypotenuse. So that original function, you could rewrite it as the square root of 1 minus 9x squared. Now, you would still need to take the derivative. Like, this is just rewriting it. This is the same thing as this. We've just rewritten it, right? We used our pre-cal skills to rewrite that original function. But taking the derivative of this is probably easier than taking the derivative of this. Remember, we have the general rule. Anytime I have a square root, the derivative is 1 over 2 of the roots. Whatever's inside would stay inside. Then your chain rule would go to the top, right? That's your power rule with a little bit of a chain rule in. That's stuff to the 1/2 power. So when you take the derivative, it would be a 1/2 stuff to the negative 1/2. So it would be a square root on the bottom. That's a derivative that comes up frequently, so you really should just know that the square root is 1 over 2 of the roots. Whatever's inside, copies inside, chain rule to the top. So here we go. We're going to take this derivative of the radical. Whatever's inside of the radical, you're going to have 2 of those on the bottom. Right, it's always 1 over 2 of the roots, and then your chain rule derivative of that inside piece, so that would be a negative 18x, would go to the top. So 1 over 2 roots would go to the bottom, and then here, your chain rule, the derivative of that inside piece would go to the top, and then look at this, the 2 and the 18, that's going to simplify, and it's going to give us the same thing. Of course it is, right? Whether you just brute force the derivative with the copious amounts of chain rule, or whether you rewrite it first and then take the derivative, you should get to the same thing. Alrighty, last one. It says, write the equation of the tangent line. Anytime you see these words, y minus y1 equals mx minus x1, right? That should just jump into your brain. We're going to write the equation of this tangent line. Here's my function. I've got f of x equals 1/2 cosine inverse of x. I just like the inverse notation. It's really the only reason is I'm lazy, and writing the little -1 exponent is slightly faster than writing the arc. The arc is probably better notation. I just have always used the -1 instead. Okay, but here's the function. It gives me the x value, and then it wants me to do this equation of the tangent line. First thing I'm going to do is I'm going to take this, and I'm going to plug it into that original function so that I can get the y coordinate. Okay, so f of negative root 2 over 2. So I got 1/2 cosine inverse negative root 2 over 2. So let's go do this thing first. I'm going to have 1/2 of it. So I'm thinking about my unit circle. There's 2 points on the circle where the x value is negative root 2 over 2. Remember the domain restrictions, I wouldn't care about that one. So I'd want this angle right here, which is 3/4. Right, so 3 pi over 4, there's your cosine inverse, and then here this y coordinate is going to end up being 3 pi over 8. That's an ugly y coordinate, but it's okay. How we find the y coordinate is we take the x and we plug it into the original. Let's set up this equation. So I got y minus 3 pi over 8 equals m, I would still need to go get the slope of the graph at that point, and then x minus, when you minus a negative, it'll change to plus, to root 2 over 2. So here's the answer. We just need to do a little bit more. We've got to go find the slope of the graph at this point, which means I'm going to have to take the derivative and then plug in my x value to it. Okay, so here we go. The 1/2 is just a coefficient. I'm going to copy it. Now, the cosine inverse is just like the sine inverse. It's 1 over the square root of 1 minus x squared. The only thing different, right, that's your sine inverse derivative. The only thing that's different is the negative. That's it. Now, I'm going to plug in the root of 2 into this. Now, instead of using the root of 2 over 2, or instead of using the negative, I'm going to use 1 over the root of 2. Because I think plugging in this, sorry, I was off the screen. Instead of using this, I'm going to use 1 over the root of 2. It's just going to make the computations a little bit faster. Okay, so f prime of negative 1 over the root of 2, it's going to be 1. So you have the negative. So you've got the 2 on the bottom. Then I'm going to have 1 minus x squared. And then what I'm going to plug in is this negative 1 over the root of 2. Okay, now let's finish this. A lot of algebra here in arithmetic. The negative doesn't matter, because when you take that negative and you square it, it's going to cancel, right? So that doesn't matter. So here I have the negative 1 on the top, that 2 on the bottom. 1 squared is 1. The root of 2 squared is 2. Let's see, 1 minus 1/2, that's 1/2. Let's pick it up down here. So I got negative 1 over 2, 1 minus 1/2, so that's 1/2. Then you have the square root of 1 over the square root of 2. So square root of 1 over the square root of 2. Square root of 1 is just 1. So we've got negative 1 over 2 over the root of 2. And then if you want to, you could rationalize, but the bottom of the bottom is going to flip to the top. So this is going to end up being negative root 2 over 2. It's coincidental. Oh, I was off the screen. So close. I've been doing good today, but oh well, so close. That ends up being the value from the derivative. It's ugly. I know most of the time we don't get ugly stuff like that. Here was the derivative. We plugged in the x value to it, and we ended up getting negative root 2 over 2. Which was just coincidental how it ended up being the same thing as the x value. That is not something that is always going to happen. We've done many tangent lines, and we know the x value and the slope typically aren't the same. They just happen to be at this point. All right, that's it. Remember, here are, I should be a little bit better, here are your formulas for today. That's how you can take the derivative of these inverse trig things. They're not super lovely. But these are things that you just kind of need to know, right? So I would pause the video if you need to, write these down, make flashcards, index cards, whatever for yourself. However y'all memorize stuff, these ugly formulas need to get memorized. Remember your sine inverse, it's 1 over the root of 1 minus stuff squared. Whatever's inside copies, then you do chain rule if you need to. The tangent inverse, it's 1 over 1 plus stuff squared. Whatever's inside copies. And then you do chain rule, and then your secant inverse, it's 1 over the absolute value of stuff. Then you have the square root of stuff squared minus 1. Of course, whatever that stuff is fills in both. And if you need to do chain rule. And then any of the co-functions, they're just the negative versions, right? These are formulas that are not super pretty, but at the end of the day, you just got to know them, right? I hate to break it to you, but those you just got to know.